Have you ever wondered how scientists design life-saving drugs? It all comes down to one fundamental rule. Molecular structure defines biological function.
To stop a virus, you must see its proteins. But there's a massive problem. They are too small for normal microscopes. They are practically invisible.
Welcome to part 1 of my protein crystallization course. Today, we'll see the invisible using macromolecular crystallography.
Let's get started.
Most biological functions are defined by interlocking molecular shapes. To design a life-saving drug, we first have to understand the specific three-dimensional geometry of the target protein. Many effective antiviral medications, like Tamiflu, were developed only after researchers successfully mapped out the physical structure of the proteins they needed to block. But mapping those atoms is a physical challenge. We need light with an extremely short wavelength to see them, like an X-ray. However, X-rays pass straight through standard curved lenses without bending, meaning they can't be focused into a traditional image. Without a way to build an X-ray microscope, scientists have to take an indirect route. They bounce X-rays off the molecule and capture the way the light scatters in different directions. This physical limitation means structural biologists can't simply take a picture of their subject. They have to mathematically reconstruct it from these scattered shadows. To get a clear signal, researchers must first force flexible, moving proteins to self-assemble into a perfectly repeating, solid crystal. The process is difficult and prone to failure. Researchers often have to engineer and test hundreds of protein variants in parallel, hoping that just one of them will form a crystal stable enough to survive the experiment. If they succeed, they hit that fragile crystal with a beam of ionizing X-ray radiation, intense enough to destroy the biological material almost instantly. To keep the protein from burning up, the crystal is flash-cooled in liquid nitrogen, a process called cryocooling, which preserves the structure long enough to collect the data. This massive engineering effort provides the raw diffraction data, but the result is a complex geometric pattern that reveals nothing to the naked eye. This is the raw data. As the X-rays hit the detector, they leave behind a pattern of dark spots. This is reciprocal space, a mathematical transform of the molecule's physical shape. To translate these spots into a 3D image with the Fourier transform, we need two properties. First, the structure factor amplitude, measured by each spot's brightness. Second, the phase angle, indicating the wave's timing. Unfortunately, upon hitting the detector, that phase information is lost. Without these phase measurements, the dots on the detector remain unresolved, leaving the molecule's structure a mathematical mystery. Since the phases can't be measured directly, scientists have developed biochemical workarounds to recover the missing information. One method, molecular replacement, uses a previously solved protein with a similar shape to provide a set of starting phases that help resolve the new data. When researchers have no prior model to work from, they have to use experimental phasing. By engineering heavy atoms like selenomethionine into the protein, they create dense, glowing marker points deep within the crystal lattice. These heavy atoms scatter X-rays differently, providing the reference points needed to calculate the missing phases. Once those phases are recovered, the math finally resolves into a clear three-dimensional map of the molecule. At this point, the Fourier transform takes the scattered data and reconstructs it into a 3D electron density map. The quality of the initial diffraction data determines the map's resolution. As we move from 3 angstroms down to 1.2, the fuzzy clouds of electrons sharpen into distinct atomic grids. The crystallographer then builds a physical model of the protein's chain, fitting each amino acid into the contours of this reconstructed map. While these structures are determined within a crystal, independent NMR tests in liquid solutions show that the core structures remain identical to their natural state in the cell. The result is a physically and mathematically verified model of the molecule's atomic coordinates. These finished models are archived in the Protein Data Bank, or PDB, making the data accessible to the entire scientific community. Since the 1970s, the number of solved structures has grown exponentially, creating a library of tens of thousands of molecular blueprints. This archive allows the pharmaceutical industry to move beyond trial and error, using these precise models to guide the design of new drugs. By understanding the exact atomic layout of a protein, we can design synthetic molecules shaped to fit specifically into a target pocket, where they lock into place and block the disease. By translating these scattered biological signals into atomic coordinates, we can manipulate the machinery of life with enough precision to fight disease at its source.